say you want us to know the hydroboration mechanism?
No. I mean, I would love for you to know the hydroboration mechanism. You don't. I'm not going to ask it on an exam.
Okay.
That always, I think, is what you guys mean by that question.
Yes, that's exactly.
Like I would love you guys to know all the mechanisms. I would like you to, take like 15 hours of credit of the mechanisms. I'd be real happy. I might be the only one who would be real happy. All right, so draw the product you get from this reaction. Ask that louder.
Do we do carbocation rearrangement necessary?
She asks about a carbocation rearrangement. That is, in fact, the point of this question. So here's what I'd ask you to do. First, just draw the Markovnikov product for this reaction. And then think about what you might get with a carbocation rearrangement.
While we wait, can we go over quickly the significance of the radical?
It just changes the mechanism.
Okay.
Right. So, the anti-Markovnikov addition of HBr is just a completely different mechanism. Right. So the point of the rule is if the reaction goes through a carbocation, you're always going to go through the more stable carbocation. There's no way to magically make it go through the less stable. That means anytime you you do a reaction, you get anti-Markovnikov addition, the mechanism has to not involve a cation. Right? So here we have radicals. With the hydroboration, we have a concerted addition and a reverse polarity. You know how in science fiction films they're always reversing the polarity? That's just what you say when you have to magically do something wrong. That's what the BH. You reverse the polarity of the HX bond, basically. Okay, so the Markovnikov product here, I guess I've been drawing that in purple. Is that. So Markovnikov product is going to be H adding to the less substituted carbon, X adding to the more substituted carbon. In this case, the less substituted this primary position, the more substituted is the secondary. But, as you say, all right, so we're going to protate that double bond. And the first thing we get, the first cation that we get is this secondary carbocation. Right, so if water attacks a secondary carbocation, we get the Markovnikov product. But we've also got hydride sitting right there that can move over there. The other thing, this is going to end up being racemic, right? Everything you learned about carbocations in chapter 7 applies to chapter 8. It's not, can't emphasize this enough, right? Reactions don't know what chapter they're in. The molecules just react like the molecules react. So carbocations are planar. The secondary cation is planar. Water can attack it from the top, can attack it from the bottom, the left, the right. And so you're going to get a racemic mixture of alcohols there. Same thing you learned in chapter 6 and 7 that carbocations can undergo rearrangements. So if you can, generally speaking, if a carbocation can rearrange to make a more stable cation, it's going to do that. So this arrow I just drew here where the hydride moves is going to give us a tertiary cation. That's way downhill in energy. Yep.
Then why would that one be the Markovnikov product if it's supposed to go through the most stable part?
Yeah, that's a good question. And this is, so Markovnikov worked in the his prime was like the 1870s. Right? So this was a long time ago. And really the fact that Markovnikov could work out the Markovnikov rule in the 1870s and 80s was superb, like amazing work. But it also means that he phrased it really badly. So probably the first organic mechanism was drawn maybe in the 1910s, maybe 20s. Lewis structures that we handle Lewis structures today. If any of you at this point, I know at this point in the semester you just took exam 2, probably people are feeling burned out on chemistry, a little down about chemistry. If we transport you guys back to 1880, you know more chemistry than anyone alive. Like leaps and bounds. Okay, so they don't have, like Markovnikov's working without Lewis structures. There's no such thing as a Lewis structure. Lewis wouldn't publish his paper on Lewis structure until 1913. Okay, so he works out this rule. He doesn't phrase it this way. He phrases the H on the hydrogen goes on the less substituted carbon, the X goes on the more substituted carbon. That is technically Markovnikov's rule. I don't like teaching it because I want to teach it so that you think about stability of the intermediate.
I think I get it. So like if it was anti and there was a peroxide, like the OH would go out totally on the outside.
Yeah, so if we did this reaction with this alkene, the OH would end up on this carbon out here. So the Markovnikov product would have the OH on the secondary carbon. The product we're going to see is actually the rearranged product. All right, so we rearrange to this tertiary carbon and then water adds. And again, the water is going to add as water, not hydroxide. I'll get out of the way in a second. Water is solvent in this reaction, so you got plenty of water. You got enough water to do whatever you want with it. And we end up with a tertiary alcohol. And this would be the major product because it goes through the most stable carbocation. It wouldn't technically be called a Markovnikov product because it's not the H adding to the less substituted, the OH to the more. But it does go through the more stable carbocation. Yes.
So on an exam or a quiz, are you going to specify between the Markovnikov and the major, or are you always going to want us to give the major?
I would, yeah, the way I would phrase that is what is the major product?
Okay.
And it gets a little, like seriously, everything you learned about carbocations applies. Remember what I said about SN1 and E1 in chapter 7. It's a mess, right? You get rearrangements. Usually if you do E1, usually if you do a reaction that goes through a carbocation, you see a variety of products. You're not usually going to see one. And so here, this is going to be major. It's not going to be the only one. And it would depend a little bit on the temperature. It would depend a little bit on the concentration of acid. It would depend on, like, I don't know. For this one, it's a straight up localized secondary versus a localized tertiary. I have no idea what that ratio would be. It's probably going to be like 70-30 tertiary alcohol to racemic secondary alcohol. Okay, so you don't have to get down. But yeah, so if that is, and I don't think I would ask a question like this because it gets really semantic. I'm not trying to teach a law class, right? But if I ask for the Markovnikov product, it would technically be this one. But if I say the major product, you got to consider rearrangements. All right. But let's say you don't want to do that. Let's say you actually want the Markovnikov product, not the rearranged product. Like I said, if we do this hydroboration reaction, I'll put that up here in green. So you might think, oh well, I'll solve this by doing hydroboration. Nope. Don't get the secondary alcohol either. All right, so the hydroboration reaction is going to do the anti-Markovnikov addition. You're going to end up putting the OH on the less substituted carbon, the H on the more substituted carbon. And you're never going through a carbocation. Right, that hydroboration reaction never has a free cation, so you don't see any rearrangement. So there's another reaction that we gotta see.
To create the Markovnikov.
To get the, if you only want the Markovnikov. And this is, I don't know if you guys will think it's a fun reaction. I think it's an interesting reaction that lets us talk about some things, and it leads into the next reaction. All right, so let me just so the reaction is not, you don't use an acid catalyst, you don't even use a catalyst, you use a stoichiometric amount of mercury acetate. So OAC that's an acetate, it's the conjugate base of acetic acid. So mercury acetate, really any kind of mercury salt, mercury 2+ salt. I'll let you guys write that down. So again, I'm not going to ask you this mechanism, mostly because of the second step. The first step, you should probably, first step you're going to be able to understand. The second step is a little weird. All right, so in this first step, again, all these reactions are using the alkene pi electrons as a Lewis base, as a nucleophile. Mercury 2+, right? That's electrophilic. And so if you look at what we get out of that, you would expect, and then you actually lose, so essentially the carbon is going to replace one acetate. And this is going to be mercury 1+ still, right? The 1+, I'm actually going to erase that. The mercury is 1+, there's one acetate that balances out that charge. Right? So you get this cation, and you might think, well, why didn't that cation rearrange? Here's why. Mercury is not hydrogen. Mercury is a really heavy element. What is it? It's 80. Mercury is 80. Any of you ever played with mercury?
That's kind of dangerous.
Yeah, why did everybody squint their eyes at me when I said that? What have you heard about mercury?
Killed isobutanol.
It can vaporize easily.
Mercury liquid vaporizes really easily, yeah. Mercury vapor is dangerous to breathe. Again, public service announcement. In general, gases are always way more dangerous than liquids and solids. Right? Gases you can't really see. You often can't see them, especially at low levels. And you breathe them in. You can't not breathe, right? You can't go in a lab and just hold your breath. We've all learned this in the last 9 months. You can't just walk around holding your breath. Mercury would go through these masks without any, mercury vapor would go through these masks without any problem. Liquids and gases could be really toxic, but you have to drink or eat them.
You mean liquids and solids?
Liquids and solids, yeah. I know what I eat. So liquids and solids might be super toxic, and if you ingest them, they'll kill you, but you have to sort of make an effort to get them in your body. Gases you can just sort of accidentally breathe, you don't know it. So mercury, and organomercury, this compound here is actually quite dangerous. Organomercury compounds are really dangerous. They accumulate in fat. The carbon-mercury bond's reasonably strong. So you've probably heard about mercury pollution accumulating in fish. There's a lot of bad stuff about mercury, and it's important in this reaction. But the other thing mercury can do, it's a heavy element. The reason I asked if you've ever played with it, as you go down the periodic table, the stuff gets really heavy, like literally heavy, like lead. Lead is way down. If you compare aluminum and lead, an equal volume of aluminum is really light compared to lead, where it's going to be heavy. All right, but the other thing it can do, mercury, like all elements beyond the second row, can expand the octet. Can make more bonds, can make a wide variety of bonds. That's why there's inorganic chemistry as a separate course from organic chemistry. In organic chemistry, we sort of keep ourselves on the second row. Elements that aren't going to go beyond the octet. Carbon is going to bond very rationally. 4 bonds. 3 different ways to do that, but there are 4 bonds. Mercury can kind of do whatever it wants. And so what happens then is instead of having a free cation, we have what's called a mercurinium ion. Right? I'm not going to get to it today, but this is going to look like the halonium ion that we're going to see when we add like Br2 or I2 or Cl2. And it's still a cation, but now it's not a secondary carbocation. Right? It's a mercury cation. It's electrophilic. The carbon-mercury bond now is really polar. Generally speaking, when carbon is bonded to a metal, the carbon, forget that. When carbon's bonded to something positive, that carbon is going to be partial positive. Okay, so we still can have water attack, and this is what happens, but we get this stabilized cation, slows the attack of the water down a little bit, but it keeps the secondary cation from rearranging. And so we don't see rearrangements. And so this gets us to the product of step 1. I didn't really do the whole mechanism here. You have water attacks and then you lose a proton, not the other way around. This isn't hydroxide attack. All right, this is the product of step 1. And obviously you don't want that mercury on there, so step 2 is this sodium borohydride reagent. You'll see more of this compound in Orgo 2. Now this is a boron that's got a full octet. It's got 4 hydrogens. But again, the polarity there is reversed. So the boron has a formal negative charge, but that negative charge is really borne by the hydrogens being more electronegatives. So you've kind of got a full negative charge spread around these hydrogens. This is not the mechanism, but a way to think about this is H- attacking there and kicking the mercury out. Right, so you've got you really do have a nucleophilic attack on the carbon that's bonded to the mercury. And that mercury winds up getting reduced. So the carbon skeleton gets oxidized, the mercury gets reduced. No, okay. So mercury, you should write in your notes that this is like a halonium ion. We'll talk about that on Monday. I've got a couple of last things to say, but that looks like a halonium ion, which is important for the next stuff we do. And it keeps the carbon skeleton from rearranging. The other thing here is, like I said, like we talked about, mercury is really toxic. generally speaking, this reaction was probably discovered in like 1930 or something. I don't know how old it is. It's really old. It's a good reaction. Carbon makes a really good bond to mercury. But on an industrial scale, if you're a company looking to make products with this reaction, you're never going to do this on an industrial scale today. Like in 1950, you could do this. You do this, take all your waste, just dump it in the ocean. Nobody cares. Today, we care. Like, and I'm not arguing against that. I care. I like tuna. I don't like to eat mercury. So, we care about that. So again, as a chemist, if you're thinking about the other way synthetic chemists can make a living today, there are a lot of processes that grew up around this chemistry, and then we discovered, oh crap, this is really ruining the environment. So you can make good money if you can figure out an alternative to that. Right? So take a reaction that uses thallium or mercury or something, these really toxic metals. Do it a different way. Do it a more environmentally sensitive way. So today, even if you're a CEO of a chemical company, you don't really care about the environment. I'm not saying that's true. Some do, some don't. The government the government charges you enough to dispose of mercury waste, and you go to jail if you just dump mercury waste. So the government charges you enough to dispose of this safely that you can use some really crazy alternatives. So today, I almost think I shouldn't teach this, because nobody does mercury reactions anymore. Maybe a little bit in academic labs, but not industrially. Industrially, we have replaced mercury with another metal. What metal do you think we might have used that is cheap? So it's cheaper to use this metal than mercury because getting rid of the waste is a lot cheaper. What's close to mercury?
Gold.
Gold. So we have generally replaced mercury with gold because it's cheaper. Gold is way more expensive than mercury. Right? There's more mercury on Earth than there is gold. But because you end up, right after this reaction, you've got all this mercury waste. And it's stoichiometric. Like for every molecule you make, you've used a mercury atom. The gold reactions tend to be catalytic, so you can just use a tiny amount of gold. And then gold is actually pretty harmless. You can drink gold. You can eat gold. You're not going to live forever. I'm not recommending it. But it's generally pretty non-toxic. Definitely compared to mercury. Anyway, things to think about over the weekend. I know you don't have much else to do. We will on